Welcome to the podcast summary of fluorine. Today's catch-up is all about fluorine, which is one of those elements that sounds niche until you realize it touches nuclear fuel, medicines, nonstick pans, semiconductors, toothpaste, and some of the trickiest pollution problems around. It's chemically extreme in a way that's almost absurd. And that same intensity is why fluorine has been both wildly useful and genuinely dangerous, from the lab bench to the atmosphere to human health. Fluorine is the most electronegative reactive element, which is a compact way of saying it pulls electrons toward itself harder than anything else in its class and reacts with almost everybody. What makes it even stranger is the paradox. Fluorine forms incredibly strong bonds once it grabs onto something, but elemental fluorine gas F2 has a relatively weak bond to itself, so it splits apart easily and attacks fast. That's why a jet of fluorine can set wood and even water on fire. And why materials people usually think of as stubborn or inert, like powdered steel, bits of glass or asbestos, can react under the right conditions. It has even bullied noble gases into making compounds, especially xenon. And under extreme conditions, there's argon fluorohydride too. So yes, even the elements once filed under basically untouchable have exceptions when fluorine shows up. Chemists suspected fluorine was its own element as early as 1810, but actually isolating it turned into a decades-long ordeal. For 74 years, researchers kept trying, and a number of them were injured or killed in the process, which is why people later called them the fluorine martyrs. That nickname is dramatic, but honestly, the chemistry earned it. The breakthrough came in 1886, when Henri Moissan used low-temperature electrolysis on potassium bifluoride in anhydrous hydrogen fluoride and finally isolated elemental fluorine. He won the 1906 Nobel Prize in Chemistry for it. And the Nobel citation called fluorine that savage beast among the elements, which feels unusually candid for official science writing. Much later, Carlo Creese showed fluorine could also be made by a chemical synthesis instead of electrolysis, even though the ingredients for that route had effectively been sitting in the literature for a very long time. Industrial fluorine is still made mainly by electrolysis, using a molten mixture of potassium bifluoride and hydrogen fluoride at roughly 70 to 130 degrees Celsius. Because pure fluorine is expensive and extremely reactive, industry often avoids shipping or storing more of it than necessary. A lot of process is generated on site, or use milder fluorinating agents instead. Its single biggest use is making uranium hexafluoride for nuclear fuel enrichment, on the order of thousands of metric tons a year. The clever part there is isotopes. Fluorine has only one stable isotope, so when you weigh UF6 molecules, the mass difference comes from whether the uranium is uranium-235 or uranium-238. That makes separation by gaseous diffusion or centrifugation possible. Beyond that, fluorine chemistry feeds into steel making, aluminum refining, semiconductor processing, high-voltage equipment, and a fluorochemical market worth well over $15 billion annually. And the mineral source behind much of this is fluoride, though about half of mined fluoride never becomes elemental fluorine at all and goes straight into steel and aluminum-related uses. A lot of fluorine's industrial magic comes from the carbon-fluorine bond, which is one of the strongest bonds in organic chemistry. That bond gives materials exceptional resistance to heat, chemicals, and water, which is why you get PTFE or Teflon, corrosion-resistant parts, electrical insulation, waterproof membranes, nonstick cookware, and fuel cell materials like Nafion. The catch is that the same durability that makes these compounds useful also makes many of them hard for nature to break down. Fluoropolymers can be valuable, relatively stable materials, but smaller perfluorinated chemicals are a much bigger environmental concern because they can persist in organisms and ecosystems for years. Fluorine also has a huge medical footprint, even though it is not an essential nutrient for mammals. About 1 in 5 modern pharmaceuticals contains fluorine, because adding a fluorine atom can make a drug break down more slowly, cross membranes better, and stay effective longer. You see that in drugs like atorvastatin, fluoxetine, corticosteroids, and fluoroquinolone antibiotics. Then there's fluorine-18, which is a workhorse for PET imaging. Its half-life is about 110 minutes, which is short but still long enough to make tracers at one site and get them to imaging centers. Fluorodeoxyglucose, labeled with fluorine 18, lights up tissues that consume a lot of glucose, including the brain and many tumors, so it's become a very practical way to see metabolism in the body. Fluoride is the more familiar everyday case. Its topical benefits for reducing cavities are well established, which is why it shows up in toothpaste and in water fluoridation programs. But the useful range is narrow, and that's part of why fluoridation stays controversial. Too little does not help much, while chronic excess can cause dental fluorosis or even skeletal fluorosis. Elemental fluorine itself is acutely dangerous. Around 25 parts per million is already immediately hazardous. 100 parts per million can severely injure the eyes and respiratory tract, and roughly 1,000 parts per million can kill within minutes. Hydrofluoric acid is especially nasty because it can seem less dramatic at first than a strong acid, but it penetrates tissue, binds calcium and magnesium, and can trigger delayed, life-threatening heart problems. Fluoride poisoning can also come from more ordinary routes, including soluble salts, insecticides, swallowing toothpaste, or failures in water fluoridation equipment. In one 1992 Alaska incident, nearly 300 people were exposed and 1 person died. And in parts of Asia and Africa, chronic high fluoride intake has caused skeletal fluorosis in millions of people. Fluorinated chemicals have been part of both major environmental progress and major environmental regret. Chlorofluorocarbons were useful because they were stable refrigerants, but that same stability let them drift into the stratosphere, where chlorine from those compounds helped destroy ozone. The 1987 Montreal Protocol sharply restricted them, and that is one of the clearer examples of global environmental policy actually changing the trajectory of a problem. The replacement chemicals solved part of that story, but not all of it. Many fluorocarbons do not deplete ozone, yet they are still powerful greenhouse gases, often with warming potentials from about 100 to 10,000 times that of carbon dioxide. Sulfur hexafluoride is one of the extreme cases at roughly 20,000, while newer refrigerants like HFO 1234YF come in far lower, below 1 compared with 1,430 for HFC's 134A. Then there are PFAS compounds, such as PFOS and PFOA, which have turned up around the world, including in human blood, breast milk, newborns, and polar bears. The full health meaning of current exposure levels is still uncertain, but their global spread, their tendency to stick around for years, and the way some accumulate with proteins have made them a very visible example of fluorine's long afterlife. Fluorine is one of those rare cases where the chemistry is almost too on the nose. The stuff is brilliant, useful, hard to replace, and a little terrifying all at once. So if the periodic table ever needed a cautionary tale with excellent industrial applications, fluorine's sitting right there. This episode was generated by Podkey. Create your own at podkey.fm.